Hello, am I audible?
Yes.
So, hello, I am Imanshu, and this is a revision tutorial. And in this tutorial, I am going to discuss the overall problems from the mechanics. So, I will start with the statics problem and then go to the dynamics. In the statics, I will try to recap the equilibrium, trusses, beams, and as well as the friction problem. And then in the dynamics, mostly I will be try to recap the relative dynamics problem like relative acceleration, relative velocity, and maybe one question from the instantaneous center and the one question I think from the rotational dynamics. So we will start with the first question, which is from the equilibrium. So here we have given the bracket which is subjected to three forces and a couple. If you represent this system by a force F, what is force F and where does its line of action intersect the x-axis? So usually in the problem of equilibrium, first we draw the free body diagram. So this is the free body diagram that we have given, and then we need to find the force F. Here the resultant force we need to find. So and we need to find where does the line of action intersect the x-axis. So there will be some line of action which is present. It could be this, it could be this, but it is given in the equation that it is intersecting the x-axis. So I'm assuming the line of action is vertical. So there is a vertical resultant force which is acting on the system, and we need to find the direction as well as the magnitude of that uh, or the component of this resultant force. So we will use the force equilibrium equations here. So let's say my force is this, or it could be this, or it could be this, right? Because only information we have given that its line of action intersect the x-axis. So it is actually crossing the x-axis, but we don't know the direction of force. We don't know what is the angle theta here. So the better way to estimate the force is to use the force balance equation, because if we use the movement equation to find the force, then we actually require the perpendicular distance from the y-axis, but we don't know this either. So this perpendicular distance d and the force is an unknown quantity. So first we will be write down the force equilibrium equation. So if I write summation of force in the x direction, then we have to consider all the force which is acting in the x direction. So it is 400 Newton and it is 200 Newton in the negative x direction, minus 200 Newton, and there will be a resultant force. This, let's say R is my resultant force which I have to find. So there is a component of resultant force also in the x direction. Let's say Rx. So this is equation 1, and from here we can get the magnitude of Rx, which is 200 Newton. Now we can do the similar thing for the forces in the y direction, and we have 180 Newton, and that's it. So it's the only force which is acting vertically. So this is my Ry. So we got to know about the magnitude of Rx and Ry. Now to find the resultant force, we can use this quotient to find the resultant force. So it will be 200 square plus 180 square. So calculating this, we will get the resultant force, which is 269 Newton. Now to calculate the distance of this force, of this resultant force, which is 269 Newton, we will use the moment equilibrium equation, because it will account the perpendicular distance. So just to recap, the moment equation in the scalar form can be given by overall force multiplied by perpendicular distance. This is given in the scalar form, and in the vector notation it is given r cross f. So when we write down the moment equation for the system, we need to consider this perpendicular distance. So by this logic, we can actually able to get this perpendicular distance, because we already know the overall forces which are acting in the system. So the only unknown quantity is this quantity, which is the perpendicular distance from the force. So if I take the moment along this point, let's say this is my point O, this h. If I take the moment along this h, we will have summation of moment along point O. So the forces which are creating the movement along this point O are this 400 Newton force, which is creating the movement, and you can see it is actually creating the clockwise movement along point O, because you can visualize that the direction of this force is actually clockwise. It's exhibiting the clockwise rotation about point O. So the movement is clockwise about point O. So for all clockwise movement, I am denoting by minus sign, and anti-clockwise movement I am denoting by positive sign. So this 400 Newton will exhibit the clockwise movement along point O. So I will write this as minus 400 multiplied by 0.6, because the perpendicular distance from this force 400 Newton and this point O is this 0.6 meter, this 0.4 plus 0.2, so it is 400 multiplied by 0.6. Then the another force which create the movement along point O is this 200 Newton force, and you can see the direction of force is toward the left side, which means it create the movement which is anti-clockwise towards O, because you can imagine the rotation of this force about point O, and it is in the anti-clockwise direction, and it has a perpendicular distance of 0.2. So the anti-clockwise I am denoting by positive sign, so it's 200 multiplied by 0.2 plus this force 180 Newton force again is creating the movement along point O, and based on the direction of this force, the direction is upside, which means it will rotate by this manner about point O in the anti-clockwise direction. So again it's anti-clockwise direction, so it's positive, so it's 180 multiplied by perpendicular distance. So if this is force is vertical, this is the vertical force, which means the perpendicular distance is horizontal. So my perpendicular distance is 0.65. Then there is an external movement which is acting here. So in the force equilibrium equation we have not account this external movement, but in the moment balance equation we can directly account this external movement. So, and you can see from this figure it is rotating in a anti-clockwise manner. So it is just 140 Newton meter equals Ry d. So Ry is some resultant force which is acting here that we have found, and it has some perpendicular distance d, and we need to find this d. So we found Ry, Rx we found which was 200 Newton, and we found Ry which was 180 Newton. So it is 180 d. So now we need to calculate this quantity. So it's minus 240 plus 40 plus 117 plus 140 divided by 180. Which is 57 by 180, which will give you 0.316 meter. So this is the direction of force Ry, or the resultant component in the y direction from point O. So this is the distance from point O for the force Ry which is acting, and the resultant force was around 269 Newton. So these are the unknown quantities we need to find out. So any doubt in this one? Push. If not, then we can move to the next problem. So it's a similar problem here. So in this problem we have the sum of movements about point A due to the forces and couples acting on the bar is 0. What is the magnitude of the couple C? Determine the sum of movement about point B due to the forces and couples acting on the bar. So in this question we have given a system, and we have given one condition that the summation of movements about point A So we have given the condition that the summation of movement about point A is 0, which means my overall summation of movement about point A is 0. And using the condition, we need to find what is the magnitude of the couple C. So this couple is acting here, which is denoted by C, and we need to find the magnitude of this couple. So we can use this condition where we write down the movement from all the forces and moments from this external couple or external movement. We take the summation of all these movements about point A and equate it to 0. So this is what we have given in the question, and when we do that we can able to find the movement at point C, because that's the only unknown quantity we have. So writing down the condition, the summation of moment about point A is 0, and then we need to figure out what are the forces which creating the moment about point A. So again we will follow the same procedure, that the clockwise is negative and anti-clockwise is positive. So now the summation of movement will have, so first this movement will contribute here in this equation. So, and you can see the direction is in the anti-clockwise direction, which means it's a positive 20 kilonewton meter. Then these forces will not contribute for a movement at point A, because you can see there is no perpendicular distance. For 5 kilonewton there is no perpendicular distance to point A, it's 0, and for 4 kilonewton also the perpendicular distance is 0, which means if my scalar moment equation is this, force multiplied by perpendicular distance, and if d is 0, then even if your force is finite, your moment at that point will be 0. So here the d is 0, the perpendicular distance is from this point of application to this point itself is obviously 0. So then this force will contribute to the movement, because there is a finite perpendicular distance. The force is finite, which is 2 kilonewton, and the perpendicular distance is also finite. So if the force is in the vertical direction, the perpendicular distance should be in the horizontal direction, and it is actually a 5 meter, right? And you can see if the force is going downward, which means it will rotate in this manner towards point A. So basically it is rotating in the clockwise direction, which means the sign is negative here, because we have discussed we will take the clockwise as a negative. You can decide your choice. You can take clockwise positive, then you need to switch the anti-clockwise as a negative. So here we take the clockwise negative, so it will become the negative 2 multiplied by 5. So basically this is F and this is D. Then this 3 kilonewton will create a movement. So again you can imagine that it is creating the clockwise rotation. So the movement direction is clockwise again, based on the direction of this force. So the direction is again downward, and it will create a clockwise movement along point A. So this is point A, along point A only. So it is again negative, which is 3 multiply, and perpendicular distance is this 5 plus 3 meter. So this is the perpendicular distance, which is 5 plus 3, 8 meters. Then we have this force, 4 kilonewton. And you can again imagine it is actually rotating in a clockwise sense about point A. So it's again negative 4, and the perpendicular distance is vertical distance, because this is the horizontal force and it is acting on the right hand side. So the perpendicular distance to the point A is this one, which is 3 meter. Then we need to find the movement. So there will be effect of this movement also at C, and you can see it's anti-clockwise direction, which means it should be positive. So there will be plus C equal 0, and we need to find this C. So we will have the equation 20 minus 10, 24 minus 12 plus C equals 0. So it will be C equals 26 kilonewton meter. So this is my unknown moment that we have found from the condition that the resultant moment at point A is 0. Now in the second part of the question we have given determine the sum of moment about point B due to the forces and couples acting on the bar. So now we need to find the moment at point B. So we need to find a moment at this point. So first we can directly take the contribution, consider the contribution of these two movements. Both are in anti-clockwise direction. This is 20 kilonewton meter and this is, we found, 26 kilonewton meter. So both are in positive, both are positive quantities, so it's 20 plus 26. And you can see now this force will not create a movement along point B. So this force 4 kilonewton here, which is given in the right hand side direction, it was creating a movement along point A, but it is not creating any movement along point B because there is no perpendicular distance uh, from this point to point B. So there is only a parallel distance but no perpendicular distance, and movement will occur due to the perpendicular distance. So for this reason, this force 4 kilonewton will not create any movement along point B, but it can create a movement along point A because there was a perpendicular distance to point A, which is 3 meter. So this force will not contribute any movement. Will not contribute to any movement. So again, this force will not contribute to any movement. This 2 kilonewton force, it was creating a movement along point A, but it is not creating movement along point B because there's no perpendicular distance. It's the only distance which is finite. It is parallel to this force. So this is a parallel distance, not a perpendicular distance. So again, this force will not create any movement along point B. So this force will create a movement because you can see this is a vertical force and the perpendicular distance to B is this, which is 3 meter. So this 3 kilonewton force will create a movement, and you can actually judge the direction as well. So it is, the force is going downside, which means it is actually rotating in the clockwise direction. So it's negative movement. So it is minus 3 multiplied by 3. So 3 is the perpendicular distance and 3 is the magnitude of force. Then these two forces will again create a moment. So earlier these two forces were not creating any moment along point A, but these forces now create the moment along point B. So this 4 kilonewton force, which is in the horizontal direction, the perpendicular distance is this, which is 3 meter, and it is rotating in this direction, which is in the clockwise direction. So it's a negative movement along point B, so it's minus 4 multiplied by 3. Then there is a force 5 kilonewton. It is acting in the upward direction, and the perpendicular distance from point B is this, which is 5 meter. And based on the direction of this force, which is in the upward direction, it is trying to rotate in this direction, which is in the clockwise direction again. So it's a negative movement. Right, now we need to solve this. So it's 46 So when you solve this, you will get 0 here. So the movement along point B, you found that it is going to be 0. So just to recap, here we have given the system, and the first part of the question we need to find the external moment at C here, which is given in this figure, given the condition that the moment at point A is 0. So we write down the moment equation at point A and we equate it to 0 to find this external moment here. And in the second part of the question, we need to find the total moment at point B at this point, and we just collect all the forces which can create the movement, and we found that the overall movement is actually 0. So any doubt in this question? So then we can move to the next question. So this is the truss problem. So here use the method of section to determine the axial forces in the members AB, BC and CE. So this is my truss. And let's say the reaction forces at A is AX and AY, and we need to find the forces, axial forces in the member here AB, BC and CE. So in these three members we need to find the force. So we use the method of section and we will cut this truss along these members. So if I cut this truss along these members like here, then we can actually focus left side of this truss, and we can use the moment and force equilibrium equations at the left side of this truss to calculate the unknown quantities. But I mean, in order to calculate the reactions like reaction AY and AX, and uh, you need to consider the whole truss. So whenever you are calculating the reactions, consider the whole truss. Once you find out the reactions, then you can apply the random cuts to the trusses. So here also there will be a reaction force such as GY. So let's find the reaction force first. So since we are going to focus on the left side of this truss, it's beneficial to find the reaction force Ay, because we need to consider this quantity Ay. So if I take the moment at point G, then I can actually calculate this force Ay, because then I don't need to consider the moment due to the force Gy, because it will be a zero, because there's no perpendicular distance from the point of force application and the point G. So the moment due to this force will be zero if I take the moment along point G, and the moment will be there due to Ay, F, 2F and Ax. Now since there is only one horizontal force here, the entire truss, I mean only one horizontal reaction force, the Ax will be zero here. By just visualization, if you do the force balance analysis, you will find the only reaction force here in the Ax is zero. So you can actually find the moment by using these three forces, Ay, F and 2F. So usual notation, clockwise negative and anti-clockwise positive. So this is clockwise rotation about point G, so it's minus Ay, and the perpendicular distance is this, which is 3 meter. Then F and 2F will create the anti-clockwise movement, because the direction of F is downward and it will rotate in this sense along point G. So anti-clockwise movement, so it's positive, so it's F multiplied by, and this is my perpendicular distance for F, which is 2 meter. Similarly for 2F, the perpendicular distance is 1 meter, but to 0. So this will be 2F plus 2F equals 3Ay. So I will get Ay as 4F by 3. Which is 1.33 F. So once I get this reaction force Ay, now I can use the method of section and I can cut along the three members of this truss. So the unknown forces we are required to find is along AB, along BC and along CE. And we have cut all these three members. So now if I do the force balance analysis in the horizontal direction, so you can see this is the horizontal force and this is the horizontal force. So AB and CE are the horizontal force. So AB plus C equals 0. So this is my equation 1. If I do the force balance analysis in the y direction, then my BC is in the vertical direction, and then I have AY, which we found 1.333 F, and we have this force as well, force F. So these three forces are there in the vertical direction. So we have AY plus BC minus F equal to 0. So my AY is 1.33 F. So my BC will be 0.33 F. This is the force in the member BC, which is 0.33 F. Alright, so we found one force along the member BC, which is minus 0.33 F. So now I can take a moment. So if I take the moment along point A, then what are the forces which will create the moment along point A? So definitely not AY, not AY and not AB. So these two forces will not create any moment along point A because the perpendicular distance is 0. But force BC and force CE will create a moment. So force F will create the moment as well. So these three forces will create the moment along point A. So the perpendicular distance for BC is this 1 meter, and similarly for force F this is 1 meter perpendicular distance, and for CE this is the perpendicular distance which is 1 meter again. So C, the direction of C we have assumed from left to right. So the movement will be along point A is in the anti-clockwise direction. It's a positive moment, so C equals anti-clockwise multiply by 1. The force F is in the downward direction, and it will along point A it will try to rotate in a clockwise direction. So it's negative. And the force BC is try to rotate in the anti-clockwise direction. So on solving this, we have CE minus F plus BC equal to 0. CE minus F plus, so BC was minus 0.33 F, so it's minus 0.33 F equals 0. So it's minus 1.33 F equals 0. So my CE will be plus 1.33 F. So this is my member at force at member CE, which is 1.33 F. So now I can use equation 1 to calculate the force at member AB, which is AB equals minus CE. And therefore the force at AB will be minus 1.33 F. At CE it is plus 1.33 F, and at member BC it is minus 0.33 F. So these are the unknown forces. So just to recap here, we have given the truss and we need to find the forces along member AB, BC and CE, and here we have used the method of section. So first step is to find the reaction forces, and once you find out the reaction forces, then you can actually use the method of section. You can split in any randomly 3 members. Here we split uh, across AB, BC and CE because these are the 3 unknown forces we need to find. So we split across these members, and then we use the force balance and moment balance analysis at left side of this truss, side of this split, to calculate the unknown forces. So any doubt?
Sir, these forces which are acting in the 3 members A, B, B, C, and C.
Yeah.
So we had assumed the direction to be acting away from the joint.
Yeah, this is purely based on the assumption. I mean, you can assume the toward joint as well, but
Yeah.
then you will get the opposite sign when you will solve the equation.
Correct. Now, if we are asked whether it is in tension or compression, so what do we write? AB is in.
So that, yeah, so that you need to check with respect to joint. So
Now
just a
we
sec.
got AB as minus 1.33 F.
Yeah. So the rule was, just a second. So basically, if it is away from the joint, then it is a tension. But if it is towards the joint, then it is a compression. So we got AB as minus 1.33 F, which means this direction was wrong. I mean, we have assumed the wrong direction. The direction should be
Correct.
this. So it's going towards the joint. So it's a compression. So AB is in compression. Then CE is positive, which means it's going away from the joint, so it's a tension.
Okay.
And BC, again, we have assumed the incorrect direction, so it's basically going towards point C, so it's compression because it's going towards point C and towards B here, so it's compression. So AB and BC are in compression and CE is in tension.
Okay.
So this is the usual method. So if this is my joint and if it is towards joint, then it's compressive force, and if it is away from the joint, then it's tensile force or the tension.
Okay. Okay. Thank you.
So let's move to the next problem. So in this problem, we need to make the shear and moment diagrams, and we have given the beam. So it's a standard problem. We have given the loading, which is the uniformly distributed load. We have given the moment, and there will be a normal reaction in the beam, and we need to find the SFD and BMD. We need to make the shear force and bending moment diagrams. So the usual practice is to make the free body diagram first and to make the shear force and bending moment diagram below that free body diagram. So first we need to determine the reaction forces. So there will be a reaction at AY, and here there will be the reaction CY. So if I take the movement along point C and equating it to 0, then it will be AY multiplied by 10, and it creates the clockwise movement. The 50 kilonewton meter is the clockwise movement, and the movement due to this uniform load is anti-clockwise, and the load resultant point load here, it will be, so the uniform load is 2 kilonewton per meter, and actually you can use the fact how it is distributed. So basically the distribution more or less look like a rectangle, right? So if you try to calculate the area of this uniform load, you actually get the resultant point load of it. So if this is 2 kilonewton per meter, sorry, this is 5 and this is 2 kilonewton per meter, then the resultant point load will be 10 kilonewton. It's like calculating the area of this shaded region, right? And in order to determine the distance, you need to calculate its centroid. So the centroid of a rectangle is always d by 2. Here in this case it's 5 by 2. So it's 5 by 2 from point A. This is 5 by 2 and this is 5 by 2. So the distance from point C is 5 meter plus 5 by 2. So the magnitude is 10 kilonewton. Magnitude of a uniformly distributed load is 2 kilonewton per meter, and its equivalent point load magnitude is 10 kilonewton multiplied by distance 5 plus 5 by 2 equal to 0. So my AY will be 2.5 kilonewton. Then we can calculate the moment, this unknown force Cy by just force balance analysis, where we balance the force in the vertical direction. So it will, AY was 2.5 minus the equivalent point load, which is 10 minus 10 plus Cy. So it's 2.5 plus Cy equals 10. So Cy equals 10 minus 2.5. So Cy is 7.5 kilonewton. So these are my reaction forces. Now we begin calculating the shear force and bending moment at various locations of this beam. So let's first consider cutting this beam at some random distance x from point A. So this is point A. Here we have force Ay, and this is some distance x. There will be a moment here m, horizontal reaction force, and this is my vertical reaction force. Right, so now we need to do the force balance analysis in this part of the beam we have considered. So the force balance is pretty easy. So first we need to find the equivalent point load, magnitude of equivalent point load of this uniform distributed load. So it will be somewhere, so as we discussed, it's usually the area of this distribution. So basically it is 2x. This is the magnitude of equivalent point load, and to find the distance, it's usually the centroid of this distribution. Basically it's resembling the rectangle, which means the centroid of rectangle will be d by 2, which is x by 2. So when we do the force balance analysis, we will get Ay, which is 2.5, minus 2x. 2x is the equivalent point load, minus v equals 0. So my v will be 2.5 minus 2x. So this is my v. So I am writing my equations in terms of x, because there is an advantage, because when you keep changing x, you will get different v, you will get different m. So for varying x, so this is your x direction. So for varying x, you can actually get different value of v, so you can actually easily plot the v here. Similarly, you can get the different value of m by varying the x. So you will get different value of m, and then you can actually easily plot the bending moment as you vary the x. Similarly for the shear force diagram. So this is the advantage of writing the shear force and bending moment equation in terms of x. So we have written down the shear force equation in terms of x. So this is only valid for for this section. It's not valid for the entire beam. So this is the shear force equation. Similarly, you can actually write down the bending moment diagram. So as you can see, if you put here x equals 0, so you will get v equal 2.5, shear force which is 2.5, which is equal to Ay, which is actually true, because here at point A your shear force is 2.5. So when you put x equals 0, you will get shear force which is 2.5. When you put x equals 5 meter, then you will get v 2.5 minus 10, which is minus 7.5, which means that at this point 5, the shear force will be negative, which is minus 7.5. Then you can randomly choose any x between 1 and 5. You can choose 1, you can choose x equal 2, x equal 3, and you can actually keep calculating the shear force, and you can just draw the points, whatever the values you are getting, and you can just plot. So at x equals 0, v is 2.5, and at x equals 5, your v is minus 7.5 Newton, or sorry, kilonewton. Similarly, you can actually calculate the moment. So for moment, you have m here, which is the unknown moment. Then you have minus 2.5 x. Now there will be a moment due to this force 2x, and it It's in the anti-clockwise direction, so it's 2x, and the perpendicular distance is x by 2. So it's 2x square by 2, basically x square equals 0. So we will get movement which is minus x square plus 2.5x. So this is the movement equation. So now again we can actually make a second cut somewhere here. So you have to make the cut after each kind of a loading. So you saw in this question we have the uniform distributing loading. So we make a cut such that it passes through that loading. Then after the uniform distribution loading, there will be a sudden change in the force. There might be a change in the bending moment diagram. So you make second cut outside it. The equivalent load was 10 kilonewton. This is x. And there will be a movement here, a shear force here. This is 2.5. Right? So now we do the usual exercise. First find the shear force by force balance. So it is AY minus 10 minus V equals 0. So it's V equals AY minus 10. So it will be AY was 2.5 minus 10. So my V will be minus 7.5. So you got V equals minus 7.5, and you can see it is not given in terms of x. It is given in terms of some value which is constant, which means that outside this uniform distributed loading, everywhere your shear force is 7.5 minus 7.5, because it's not changing with x. It's not given in terms of x, so it's independent of x. So until until this point B, it will change with respect to x by this relation 2.5 minus 2x. Outside B, it is minus 7.5 everywhere, which is what your equation is saying. Then you can calculate the moment. You equate it the moment equal to 0. Then you will have, so this distance is x minus 2.5. So we'll have m minus 2.5x plus 10x minus 2.5, and there was some couple as well. This 50 kilonewton meter, this couple was acting here, plus 50 equals 0. So your m will be, when you solve this, simplify this equation, you will get m, which is 7.5x minus 75. So this is the bending moment outside the uniform distribution load. So inside until this point B, it will try to obey this relation, and beyond point B it will try to obey this relation. So based on this relation we have obtained, now you can actually draw the bending moment diagram and shear force diagram. So when you keep putting or keep changing the value of x here, here and here, you will keep getting different values of bending moment and shear force, uh, value of shear force. So based on that you will get something here. So here at point A we know it's 2.5 shear force, because here we got 2.5 at x equals 0. So here it is 2.5. Then at point B, this is your point B, it's minus 7.5. This is minus 7.5. So it is varying like this. And you can see that the variation, it's 2.5 minus 2x. This is the variation of shear force, 2.5 minus 2x. So from the equation you can see it is varying linearly. It's not like minus 2x squared. So if it is 2x squared, then there here should be a curve like this. But it is minus 2x, which is it's varying in a straight line manner. It is varying linearly as a straight line. So there will be a straight line like this. And after point B we found it's minus 0.75, sorry, minus 7.5, and it's a constant. So this once at B it reaches minus 7.5, and after that it is minus 7.5, which is constant. So this is your shear force diagram. And similarly you can actually make the bending moment diagram. So from in the region AB, it will try to follow this equation, and you can see that it is x square. There is a x square term, so it will not vary in the straight line. It will vary in the curve x square, because there is a term x square. So it will vary like this. If you keep changing x value, you will get different time value. So this is 12.5 and minus. Then due to this couple, there will be a sudden change in the bending moment. And here between region B and C, you can see it is given as 7.5x. This is positive 7.5x plus 75, and now it will vary linearly. So this is the bending moment diagram. And this detail about the variation can easily deduce from the obtained equation. When you solve and obtain the equation, then you can easily deduce the SFD and BMD. So any doubt? So if not, then we can move to the next question. So here we have given the masses of the blocks, which are MA 30 kg and MB 70 kg. Between all of the contacting surfaces, we have the coefficient of friction 0.1. What is the largest force F that can be applied without causing the blocks to slip? So we actually solved this kind of problem in the previous tutorials when we were discussing the problems of friction. We solved very similar problem related to that. And in such problem we have discussed that we need to separate the analysis according to the number of system given. So here we have given two boxes. That means first we have to solve for the free body diagram for the block A only. Then we need to take separately box B. We need to make the free body diagram separately for box B, and then we need to solve for box B. So if I consider box A, this is force F. There will be a reaction forces which is acting, and the friction force here which is mu s r. There will be one reaction force due to block B, which is P, and the friction force mu s p. And then there will be a weight which will be acting mg, and this angle is 20 degree, which is given here. So this is the free body diagram of block A. Now once we draw the free body diagram of block A, we can use the force balance analysis. To find the unknown force. So if I do the force balance analysis in the x direction and assume it's in equilibrium, then I will have minus F sine theta due to this plus R plus the component of this friction force, which is mu sp cos 20. It's a horizontal component, so it's mu sp cos 20, and then component of this force P. So it's not a vertical force, it's acting at an angle. So this is 20. So it's P sine 20. So this is my equation. And you can see there are three unknowns in this equation, F, R and P. So we can write down another equation when we do the force balance analysis in the y direction. So this is my x, this is my y. So in y we have a component of this force F, component of this force mu s p, and component of this force P, and this weight of force mg. We have this force as well, mu s r. So this is my equation 1 and this is equation 2. So you can see that there are 3 unknowns but we have 2 equations. So let's draw the free body diagram of block B. So we get 2 more equations. So in that manner we can actually solve for the unknown quantity. Because as of now we have only 2 equations but we have more unknowns, so we need more equations to solve for the unknowns. So this is P, this is mu SP, this is mg, this is the normal reaction. So you can see one more unknown will come here due to this normal reaction M. So overall there will become 4 unknowns and 2 more equation will come due to force balance analysis on this block B. So there will be 4 equation overall and there will be a 4 unknowns. So we can easily solve for the unknowns then. Right, so these are the forces which are acting. So now we can do force balance in the x direction and we will get say 20 mu Sn and component of mu Sp as well. So this is equation 3, and when we do the force balance in the y direction we have minus P cos 20 minus mdg. So this is mass of block B and this is mass of block A. Plus n minus mu Sp sine 20 equals 0. Right? So just to recap here, earlier we have got 2 equations but we got 3 unknowns. So we couldn't solve these 2 equations together. So so next we also considered block B where we get 2 more equations and we got 1 more unknown. So overall we got 4 equations and 4 unknowns. So now we can actually use all these 4 equations to calculate all 4 unknowns. So the unknown quantities are F, R, P and N. So these are 4 unknown quantities that you can actually solve by using these 4 equations. So when you solve these equations you will get F 197 Newton, N which is 1130 Newton, R which is 212 Newton and P which is 456 Newton. So this you will get when you solve all these 4 equations. So if you have any doubt in this question. If not, then we can move to the next part. So here we have given a gear which rotates with angular velocity omega, which is 10 rad per second, and the gear rack moves at velocity vc, which is 5 meter per second. Determine the velocity of the slider block A at the instant shown. So we actually solved these kinds of problems a lot in the previous tutorials. So we have discussed that, let's say if you have given a system with different component of the systems, let's say this is A, B and C, and it doesn't matter what is the motion of A. It can be rotating motion or it can be a translating motion. So once you have given the details about the motion of point of body A, you can actually calculate the motion of body C and motion of body C. Whether it can be either a rotational motion or it can be a translating motion. And this usually you do by using the expression for the relative velocity concept. So when you use the concept of relative velocity, you can actually find the motion of one body when you have already given the motion of another body, and all these are connected to each other. So here in this question we have given the motion of this rack C, and we have been asked to find the motion of body A. We have also given the motion of this body, which is, let's say, B. So this is body B. So this C is actually having a translation motion and it has VC. Then this VB actually having both rotational and translation motion. So it is rotating and it can also move in left and right direction. So it has both translation and rotational motion. And A is having some translation motion. It doesn't have rotational motion, but it is having some translation motion. So for this you can actually use the relative velocity concept. So for example here, let's say you have given the motion of body A and you need to find the motion of body B. So you can actually write down the expression for velocity of motion B, given that you have already know the motion of A plus the relative velocity of B with respect to A. And the relative velocity of B with respect to A can be given by omega cross position vector. So this is the relative velocity of B with respect to A. So we will use this concept twice. First we will try to know the motion of B, given that we know the motion of A. Then we will again use this equation to find the motion. So first we will be using this equation to find the motion of B, given that we know the motion of C. So here we know the motion of C. Then we will use the same equation again to find the motion of A, given that we know the motion of B. So first let's find the velocity, translation velocity of B, given that we know the translation velocity of C, which is 5 meter per second. Right, so VC is 5 meter per second and it is in the x direction, minus x direction. So it is minus 5 in the x direction, and omega is 10 rad per second, right? And the direction of this angular velocity is coming out of the screen, so it's a k direction. So this is x, this is y, and out of the screen is z. So the direction of this angular velocity is out of the screen along the z direction. So it's minus 10k. It's a clockwise, so I'm writing minus sign here. And it is having a cross product with position vector RBC, and it's 75 mm. It's in the j direction. Right? So in the vector, when you write down the cross product, so in the vectorial form you can actually easily calculate the cross product. So it's a cross product of between k and j. So if you do the cross product between k and j, you will get ith component in the x direction, and the magnitude you just multiply 10 with 0.075, it will be a minus I, so it will be plus, so it will become 0.75 I. So now both are in the x direction, so it will be minus 4.25 I. So this is the translation velocity of VB, which means this gear is rotating and also moving in the left direction with velocity VB, which is 4.25 meter per second. Now as this gear is moving in the left side direction, it creating the motion, upside or downside motion of this body A. And now we need to find the velocity of this body A. And now we already know the velocity of this body B, so we can use this expression between A and B. Earlier we have used between B and C, now we can use this expression between A and B. So VB is minus 4.25 in I direction, and this is omega cross position vector A cross B. So this omega is now the angular velocity of this rod, right? And the position vector is 0.5. So it's 0.5. So let me first erase. So if this is my 0.5, then this is 0.5 cos 60, and this is 0.5 sin 60. So this will be my position vector for 0.5 cos 60 in the x direction, 0.5 sin 60 in the y direction. So it is minus 4.25 I plus omega cross 0.5 cos 60 I plus 0.5 minus 0.5 sin 60 j. So this is my position vector, and I don't know the omega. I don't know the angular velocity by which this rod is rotating. But I know the direction of this omega, it's in the z direction. Okay. So when you take the cross product between k and I, you will get some quantity in j. So it's 4.25 I minus, and the magnitude is omega multiply 0.5 cos 60. So omega multiply 0.5 cos 60 in j direction. When you do the cross product between k and j, you will get something in the ith direction, and the magnitude is omega multiply 0.5 sin 60 in the ith direction. So now there are two quantities which are in the x direction. So these are in the x direction, and
The last one will be negative.
this one,
No, this omega into 0.5 sin 60.
uh, due to this thing, k cross j.
Yeah,
Yeah, I suppose. Yeah. So So now I can use the fact that, so in the previous classes we have used the fact that, for example, let's say this is O and this is point A and it is actually rotating. So you actually, and this is the radius r, so you can actually get the velocity of at point A by using the relation omega multiply by r. So basically I am writing in the scalar form. So by this expression you can actually get the translation velocity of this point A, given that it is rotating with some angular velocity omega and there is a distance r. So I can use this concept at the left hand side here, which I write in terms of omega cross r. No. So we can use the fact that here, so you can see here that there is a translation motion at point A. So this can either go upside or this can either go in the downward direction. But this system, since it's a constraint, it's between the walls, it cannot move in the horizontal direction, which means whatever the velocity, vector velocity of point A you will get, it will be in the y direction. It can be written in j cap quantity only. So in the horizontal direction your velocity vector is 0. I mean the magnitude of this velocity is 0, but which means the only direction of this velocity vector A is in the y direction, because in x direction it cannot move because it's between the wall, it's a constrained motion, right? So this velocity vector entirely given in the in the y component. It's the x component of this velocity A is 0 because it's a constant motion. It can only go in upside and downside direction. It cannot go in the horizontal direction. It cannot move in the x direction, which means now I can split this equation in the x and y form. So you can see this is in x, this is in x, and this blue color is in y direction. And this VA can be written in terms of y component only, because there is no horizontal motion, so this horizontal component is 0. So if I write the horizontal component of this vector equation, so it will be 0 equals minus 4.25 minus omega cross 0.5 sine 60. So in that manner I can actually calculate the omega. So it will be 4.25 equals omega 0.5 sine 60. So the omega you will get 9.815 rad per second. It's in the negative sense. So once you get the omega, the angular velocity of that rod, now you can again write this equation in terms of y component. So in terms of y component you will only have VA equals minus omega 0.5 cos 60. So omega is minus 9.815, so it will be 9.815 multiplied by 0.5 multiplied by cos 60. So your VA will be 2.45 meter per second. So this is the required velocity we need to find. So just to recap here, we have given a system with multiple connected links. These are A, B and C. We have given the translation velocity of C, and we have been asked to find the translation velocity of A. So first we connect system C and B. We have given the translation velocity of C, so we found the translation velocity of B. Then we connect system A and B, and by knowing the translation velocity of B, we can able to find the translation velocity of system A. So when you have velocity given for any given system, you can calculate the velocity of another system by using the concept of this relative velocity. So this types of problem we have solved in the tutorial where we have discussed such problems. So any doubt in this problem? If not, then we can move to the next problem. So here it's a similar problem. The only difference here is the frame of reference in this problem is rotating. So in the previous problem it was fixed. So we have worked on the fixed frame, but now here we have a multiple frame of reference. We have a fixed frame as well as we have a rotating frame, and you can actually visualize this concept in this problem. So you can see there is a fixed frame along this axis. If you define this axis as capital Z, then along this axis this can be treated as a fixed frame. But now if you need to find the velocity of this collar, let's say C, and if this AB is rotating, then you can imagine that this problem is the concept that you need to use in this problem is of rotating coordinate system or the moving coordinate system. So your coordinate system is moving, and you need to find the velocity of a component which is placed on a coordinate system which is rotating. So here you need to find the velocity of collar C, which is placed in a coordinate system which is rotating. So this coordinate system is aligned with AB, and this AB is rotating, which means this coordinate system which is aligned with AB is rotating, and the collar C is actually placed in that rotating coordinate system. So it's the same problem that we have discussed, but with a fixed and rotating coordinate system. So there will be a little change in the equation here. So we will use the same equation, but we will also consider the effect of rotating coordinate system. So here in this question we will assume that at a given instant my rotating coordinate and fixed coordinate will align. So this is at a given instant, and we need to define the velocity and acceleration of a collar C. So we will be writing the equation. So it is Vc equals Va plus omega AB cross R C with respect to, sorry, it's B, respect to B, plus the contribution of the relative velocity. So this small xyz is moving coordinate system, and capital XYZ is fixed coordinate system. And these velocities are defined in fixed coordinate system. And this is the rotation of a coordinate system itself. So if my coordinate system is aligned with respect to AB, then this is the rotation of a coordinate system AB. Right, and this collar moves, it's given in the question that the collar C moves along rod BA with a velocity of 3 meter per second. So along the rotating coordinate system, along this rod AB, along this rotating coordinate system, because our rotating coordinate system is aligned with AB, so this is A and this is B, so our rotating coordinate system is aligned with AB, and it is given in the question that collar C moves along rod AB with a velocity of 3 meter per second, which means along the rotating coordinate system my collar velocity is 3 meter per second, which is my relative velocity. Right, it's a relative velocity because the collar C is moving and this whole rod AB is also moving, so there is a relative motion between the motion of AB and the motion of C. So the relative velocity is along small y and capital Y axis. So this quantity you need to write in the rotating frame of reference. So it is given in terms of 3, and when you write down in the vector notation it will be 3j. So if I write down this equation, it is Vc. Now velocity at point B, translation velocity at point B is 0 because it is fixed. It is not moving or translating in any direction, it is only rotating. So the translation velocity of Vb is 0 plus 6k. Now 6k is the angular motion of the rod AB and it is in the Z direction. And then we need this position vector RC with respect to B, which is this direction, which is 0.5 in the J direction, plus 3j. So this will be my velocity vector C. So between K and J I will get the component in minus I direction, and the magnitude is 6 multiplied by 0.5, which is 3. So the velocity vector at C will be minus 3i plus 3j. So this is the velocity of collar C in the fixed frame. In the fixed frame, in the question we have given the velocity in the rotating frame. Now we have found the velocity of collar C in the fixed frame with respect to fixed frame. Then we can find the acceleration as well. So acceleration of point C will be given as acceleration of point B plus omega dot AB cross RC with respect to B plus omega AB plus omega AB plus RCB plus 2 omega AB cross relative velocity in XYZ plus relative acceleration in XYZ coordinate. So this is the Coriolis acceleration which occurred in the rotating frame of reference only, and this is the relative acceleration in rotating frame, and this is in the fixed frame. This is also in the fixed frame, right? So the relative velocity and relative acceleration we have given in the question. So it's a 0.5 meter per second square. So this is, so first we need to figure out all the terms, because we just need to substitute all the terms in this equation to find the acceleration. So we have to make sure that we know about every term. So relative acceleration we have given in the question, which is 0.5 j. We have given the angular velocity, which is 6k, and we have given the angular acceleration here, which is 1.5 rad per second square, which is omega dot ab, which is 1.5 k. So we know this, we know this, we know this. So we know all the quantities which are required in this expression. AC will be AB is 0, because there is no translation velocity, so no translation acceleration of point B. Omega dot is 1.5 k cross position vector RC with respect to B, which is 0.5 j plus 6k cross 6k cross 0.5 j, which is this quantity. Then there will be a Coriolis term, which is 2 omega AB, which is 6k cross with relative velocity, which was 3j, and the relative acceleration, which is 0.5 j. So now you got the equation, vector equation, you just need to figure out. So it is k with j will give you minus I, and the magnitude is 1.5 by 2. So this term will give you the direction minus I, and the magnitude is 3. Then you need to do cross product between 6k and minus 3I, will give you j direction, and magnitude is 18, overall minus 18. So it is minus 18 j. Then this will give you minus I, and the magnitude is 36, minus 36I, and this is plus 0.5 j. So you will get a vector which is minus 36.75 I minus 17.5 j. So this will be your acceleration vector. So this is your acceleration of point C in the fixed frame, and this is the velocity of C in the fixed frame. So any doubt in this question? If not, then we can move to the next question. So here we have given a 5 kg cylinder which is initially at rest when it is placed in contact with the wall B and a rotor at A. If the rotor always maintains a constant clockwise angular velocity omega, which is 6 rad per second, determine the initial angular acceleration of the cylinder, and the coefficient of kinetic friction at contact surface B and C is given, which is 0.2. So in this question we have given the mass of the cylinder and we need to calculate the angular acceleration. So we have discussed that the force for the non-zero acceleration, there will be an external force which is acting on the system. Similarly, if you have a non-zero acceleration, then there will be a non-zero movement which is acting on the system. So this problem requires the combination of statics and the kinematics. So basically this problem belongs to kinetics, where we use the concept of statics and kinematics to solve the problem. So earlier in the statics part, we have solved a problem where we say that my force, overall resultant force, equal to 0 and my resultant moment equal to 0. But now since we have given the non-zero acceleration in the system, here the resultant force is equal to ma and the resultant moment equal to moment of inertia multiplied by angular acceleration. So first we made the free body diagram. So it's 5, so weight 5 into 9.81. There will be a normal reaction NB. There will be a friction force which is 0.2 NB. Then there will be a normal reaction here which is NK and the friction force 0.2 NA. This is X, this is Y. And my moment of inertia is 1 by 2 mr squared, so it is 1 by 2 5 multiplied by r square, which is 0.125 square. So your moment of inertia will be 0.039 kg meter square. Then if you do the force balance analysis in the x direction, equate it to max. So you can see it cannot move in the x direction because of the constant here. So there is no translation motion in the x direction, so your ax is 0. So basically it will turn down to a fx equal a. It's an equilibrium in the x direction. So it will be, if you do the force balance analysis, it will be NB plus 0.2 NA cos 45 minus NA sin 45 for 0. So this is equation 1. If you do the force balance analysis in the y direction, it is MAY. Right, again there is no translation motion, so this cylinder can rotate due to this, but it cannot perform translation motion, so AY is also 0. So this, and the resultant vertical force will be 0.2 NB minus 0.2 NA, sorry it is positive sin 45 plus NA cos 45 minus 5 into 9.81 equals 0. This is equation 2. And then you can write down the equation for moment balance, which is equal to I alpha. And we have given the alpha which is non-zero. And we need to determine the angular acceleration, so we need to determine alpha. So the summation of moment will be due to the forces 0.2 NA, this 0.2 NA. So here I have taken the moment along point O, along this point O. So there will be a moment due to this force 0.2 NB, there will be a moment due to 0.2 NA. That's it, this two force only will create a movement along point O. So first we'll create a clockwise movement, and this will create a anti-clockwise movement. Point 2 Na will create an anti-clockwise movement. So it is positive 0.2 Na multiplied by 0.125 minus 0.2 Nb multiplied by 0.125 equal to I alpha, and moment of inertia is 0.039 multiplied by angular acceleration. So this is equation 3. Now you can solve equation 1 and equation 2 together to calculate Na and Nb. Once you calculate Na and Nb, you can substitute in equation 3 to calculate alpha. So when you do that, you have Na which is 51 Newton, Nb which is 28.8 Newton, and when you substitute this into equation 3, you will get alpha which is 14.2 rad per second square. So this is your angular acceleration. So just to recap here, we are given a cylinder here which is tend to rotate, and we need to find the angular acceleration of the cylinder. We have given the mass of the cylinder, angular velocity, and the friction forces which are acting at the surface between cylinder and the wall. So from this data we actually inspect that we need to solve for the force balance equation, and here the force balance equation or the movement balance equation is not in equilibrium. So for this question, the movement balance equation is not in the equilibrium because it is actually having the finite angular acceleration. So you may find a problem where it is actually exhibiting the translation motion. In that case, these acceleration are non-zero, and instead of 0 in the right hand side, it is given in terms of accelerations ax and ay, which can be unknown or which can be given in the question depending on what they have been asked to find. So in such question, the force and moments are not in equilibrium, so the right hand side are not zero. It is given in terms of the kinematics quantity like velocity, acceleration, and so on. So usually the force is written in terms of acceleration according to the Newton's second law, and the movements actually written in terms of the angular acceleration according to the Euler equation. So once you connect the statics quantity and the kinematics quantity with each other, then you can actually find unknown forces, or you can actually find some unknown quantity from kinematics. So once you calculate this acceleration, angular acceleration and translation acceleration, you can even calculate the velocity and the distance it's moved by using the kinematics equation. For example, you can use v equals u plus at. In case there is a non-zero acceleration, you found the acceleration by using these two equations. Once you get the acceleration, then you can use this equation to find the velocity or time and so on. So there is a good connection between statics and kinematics using these equations. So that's it for today's class. So basically we have discussed a lot of problems from statics and some problems from dynamics. So yeah, thank you.
Thank you so much.